So, what does the big history story tell us? Here is a very, very short version of that story. Our universe appeared about 14 billion years ago. It appeared in ways we do not fully understand, as a tiny, concentrated ball of energy, smaller, much smaller than an atom. That ball of energy was very, very simple, but it contained all the energy that is in today's universe. So it was unimaginably hot. Like an explosion, it expanded, and as it expanded, it cooled. And as it cooled, new types of things congealed out of the fantastically hot cloud of matter, of energy. Matter appeared in the form of quarks, which combined to form protons and neutrons. Electrons appeared, and within a few 100,000 years, the first atoms appeared. Most were very, very simple. They were hydrogen or helium, the simplest atoms that can exist. Gravity sort of crushed atoms together so tightly that they began to fuse. Think of what happens inside a hydrogen bomb. As they fused, they released colossal amounts of energy and created an entirely new type of object, the first stars. These lit up a few 100 million years after the Big Bang. You'll soon get used to the idea that a few 100 million years is not really terribly long, or a few 100,000 years. Stars gathered together in huge crowds to form galaxies and began pumping energy, light, and new types of matter into the space surrounding them. So gradually, the space inside galaxies became more and more interesting. Inside stars, atoms fused to form new elements, such as carbon, or oxygen, or iron. When stars died, they often blew up in supernovae, creating even more elements and scattering them through space. And there, in the space between stars, atoms combined to form new types of matter, such as water, ice, dust, and even molecules such as amino acids that are the keys to life on Earth. Atoms of dust and ice and rock orbited newly created stars in what astronomers call protoplanetary disks. That, by the way, is one of the earliest photographs astronomers ever took of a protoplanetary disk. New planets are being created there around a young star. Inside those protoplanetary disks, rocks, ice, other materials stuck together to form meteors, asteroids, and eventually planets. And this is how our solar system emerged, about 4.5 billion years ago, with its own star, the Sun. Our home planet, Earth, was formed as part of this process. But Earth was unusual because it contained many different types of matter. Its temperatures were just right for more complex molecules to form. These were Goldilocks conditions for the creation of life. And life meant a new level of complexity in the universe. I hope you see what's happening. A universe that was extremely simple when it first appeared is slowly filling up with more and more complex and interesting things. And that process is what eventually allowed us to exist. About 4 billion years ago, life appeared on Earth. We now understand a lot more about how life emerged, more than we did 13 years ago, but we still don't have the full story. Life may also exist elsewhere in the universe, and for what it's worth, my money is on the idea that it does exist in lots of places in the universe. But we may learn within our lifetimes, if there is life near us, from telescopes such as the James Webb Orbiting Telescope. Life is extraordinarily complex. So defining life is not easy. That's partly because living things are built from very complex molecules, such as proteins and DNA. But what is particularly interesting about living organisms is that, unlike rocks or stars, they act with purposes and goals. Now, I love this picture because this is clearly an animal that's going to act with a lot of purpose and with a lot of goals. Their most basic goals, and you and I share these goals, are to survive and reproduce. And those organisms that reproduce pass on to their descendants the genetic recipe for survival and reproduction in a particular environment. Now, that environment could be deep beneath the ocean at volcanic vents, or it could be in trees in the Amazon forest. The first living organisms on Earth were single-celled bacteria. But over time, tiny copying errors in reproduction allowed new variants to evolve, and some of them found new ways of surviving and reproducing. And in this way, living organisms began to spread through the oceans of planet Earth and eventually onto the land, where they turned brown landscapes green. In the last billion years, much more complex organisms evolved. They were built from huge numbers of individual cells that worked together for the good of the larger organism of which they were a part. Multicellular organisms like you and me are colossal. Comparing a bacterium to a human, I think, is a bit like comparing the Burj Khalifa to an ant crawling along its front steps. We humans are made from trillions of cells that collaborate with astonishing efficiency because they share the same DNA. And their collaboration, by the way, has a lot to teach us humans today. Our species evolved just a few 100,000 years ago, which is an eye blink on the timescales of big history. In a sense, we're just one more of billions of species that have inhabited this planet. Yet we're also one of the strangest of all the species that have called Earth home. It's much easier to see how strange we are through the wide-angle lens of big history. This is what makes us so strange. Most species seem content to live in a particular niche. Koalas, for example, chew the leaves of a few types of eucalyptus trees. That's how they survive and reproduce. What makes us humans exceptional is that in our brief time on Earth, and yes, a few 100,000 years is not long on the scales of big history, we have managed to live in more and more environments. By 10,000 years ago, humans could be found on every continent apart from Antarctica. Then, through agriculture, humans began reshaping the Earth's landscapes in ways that could support more and more humans. Until today, as you know, there are 8 billion humans on planet Earth. 200 years ago, humans discovered the colossal energy locked up in fossil fuels. And in just my lifetime, we have used this bonanza of energy from fossil fuels to transform the surface of planet Earth. We've changed its landscapes, its climate system, its oceans, and we're even cluttering up the space above our atmosphere with human junk. Then, less than 100 years ago, we learned how to create weapons of mass destruction that could ruin much of the biosphere in just a few days. Now, let's be clear, nothing like this has ever happened before in the 4 billion years since life first appeared on Earth. What that means is that we live at a momentous turning point in the history of our planet. We've entered what many call the Anthropocene epoch, in which we humans seem to dominate change on Earth. This is remarkable, but it's also dangerous and very, very worrying. But the big history story can also tell us why we are so powerful. And by doing so, it can point to possible ways of ensuring a better future. So let me now tell you the optimistic story that I believe is embedded within big history. Let me begin with a question. Why are we humans so much more powerful than any other species that has ever existed on Earth? The key, I believe, is human language. All living organisms learn about their environments. But animals with brains can learn much more because brains use limited sensory information to construct models of the world by interpolating, by guessing what might be there. Those models can tell a deer or an antelope that just a few hints of yellow and black stripes are probably a tiger. So look out. Some animals have languages, and that means they can learn much, much more about the world by sharing what they know with other members of their species. And these shared visions of the world are much, much richer than the visions of individuals. To get a sense of how much richer they are, just imagine for a moment how limited your understanding of the world would be if you had never, ever spoken to another human being. You would be aware only of what was immediately in front of you. What makes us humans so different is that our languages are so powerful that the sharing of information about our world has virtually no limits. We can pass on our grandparents' knowledge of herbs, or, if we lived 10,000 years ago, how to hunt mammoth. And we can learn new things from strangers and pass them on in stories. New information means we can exploit our surroundings more and more effectively and spread into new environments. Other animals with language, such as chimps or orcas, seem incapable of spreading beyond a limited number of environments. But we humans share ideas and information so prolifically that in the course of human history, we have spread to more and more environments until today we're transforming planet Earth. These shared visions of the world that make us so powerful began as shared visions within particular tiny communities early in human history, and they're unique to our species. I call them core stories. They include much of what today we call religion, science, philosophy, and many other forms of knowledge. Core stories assemble all you need to know to survive in a particular society, all its scientific knowledge, its moral knowledge, and its rituals and traditions. Because they're shared, core stories enable whole communities to work together with common goals and purposes. In addition, each core story can accumulate more knowledge over time, particularly by sharing knowledge with neighbouring communities. That is what has driven our remarkable capacity for sustained technological innovation since our species first appeared a few 100,000 years ago. And this graphic shows some of the critical technological innovations of the Paleolithic era, which we often don't take seriously enough. Over time, the core stories of different communities have slowly enriched each other, and eventually, some of those core stories began to overlap. If there was enough overlapping, different core stories might eventually merge to form a new core story for a much larger community, such as the core stories of the Muslim world or China. But the merging of core stories was often extraordinarily painful. Many people resisted changes to their core stories for understandable reasons, creating conflicts that could be extremely violent. We see plenty of evidence of these conflicts today. And the blood bias of most of today's media focuses mainly on those conflicts, creating an excessively pessimistic and depressing account of the world. The impact of that view of the world is apparent from the following chart, which shows, amongst other things, that at the time the survey was taken, 74% of young Indians thought humanity was doomed. But look beneath the surface. Try to put aside the blood bias, and something much more promising is happening. New technologies such as planes, the internet, and smartphones are linking people all around the world, so that core stories are now overlapping on a global scale. And those processes are slowly creating an embryonic core story for all of humanity. Modern scientific ideas have now become part of every core story in the world. Look at the syllabi of modern schools. They are similar in ways that were unimaginable just 100 years ago. Look also at the convergence of moral principles in documents such as the Sustainable Development Goals of the United Nations, or the remarkable fact that in early 2024, 127 countries had committed to reaching net zero greenhouse gas emissions. Or look at the many conversations between religions that are revealing more and more common moral principles. Or look at emerging global rituals, such as the annual fireworks displays at midnight on New Year's Eve. I watch those every year from my house in Sydney. Or look at this global gathering of representatives of governments from all over the world. Building and nurturing a global core story has become a matter of great urgency because it can help us solve one of the fundamental challenges of our time. Can all humans work together despite being divided into competing nations and civilizations? Only if we share a common vision of the world, as the cells in our body share their DNA, will we be able to collaborate on building a good future for all humans and for the whole biosphere. So this is the challenge we face today. Can humans bridge the gap between the interests and perspectives of regional communities and those of humanity as a whole, so that they can work together to avoid catastrophe and build a better future?